All right, let's do problem number 69. A uniform, hollow, cylindrical spool has inside radius r divided by 2, outside radius r, and mass m. It is mounted so that it rotates on a fixed horizontal axle. A counterweight of mass m is connected to the end of a string wound around the spool. The counterweight falls from rest at t equals 0 to a position y at time t. Show that the torque due to friction forces between the spool and axle is this thing. As always, we start off a diagram, so I'm just going to copy the diagram in the book to start. This is big M for the mass of the spool, and if you didn't catch on the problem, the spool is actually the thicker cylinder, and this is the axle. And this is our mass, and that's supposed to be lowercase m. So the question asks you to find the torque due to the friction forces between the spool and the axle. So where exactly is this torque that they're talking about? Where's this friction torque, as we'll call it? Well, if this mass is wound to the spool, this mass is it has gravity, so it's gonna actually pull the spool down and apply the torque in this direction. And I'm sure you can visualize that. And we'll call it tension because that's a string. So the torque due to tension is gonna be in this direction because it's gonna pull it down. And since friction is in the opposite direction of motion, you can see that in between, you can imagine an axle and a cylinder rotating around it. There's going to be friction along the axle. So the friction is going to be right there. And we'll call that, it's going to be the opposite. So it's going to be twisting that way. And that torque will be, we just label it torque due to friction. And so in order to solve for the torque due to friction, you simply sum up your torques, like how you would sum up your forces in a force problem. So sum of your torques is torque due to tension. So we'll make positive the direction of motion. So this is going to be positive motion, and this will be negative motion. So I'm going to do torque due to tension minus the torque due to friction. And the equivalent of ma would be moment of inertia for mass and alpha for acceleration. All right, once you're here, just isolate your torque due to friction. Once you isolate your torque due to friction, you get torque of friction equals torque due to tension minus moment of inertia times alpha. So recognize that torque, the formula for torque is actually the force times radius sine theta. And since these torques are being applied in a in a 90-degree angle, you don't have to worry about sine theta. So all you really have to worry about is F and R. So F for the torque due to tension is actually going to be just T times radius R. But why big R? What's up with these like R over 2's? Well, looking at this diagram is actually a little bit complicated. To actually get a better sense of the problem and why you use big R for here, imagine you're looking at this from this angle, like you put a camera here looking for this angle. So if you get a cross section of this, it's gonna look like this, right? This is the cross section. And this is the center right here. This is your torque due to friction, and this is your torque due to tension. As you can see, it doesn't matter that you got that axle there. The torque due to tension, the radius to the center of this entire apparatus is still big R. So that's why your torque due to tension is just TR. So in place of torque due to tension, you write TR. So let's rewrite this. Torque due to friction is equal to TR minus moment of inertia alpha. Once you're here, you realize that you have 3 unknowns. 3 of these variables are not given in the problem. The following are not given. Tension, a moment of inertia, or alpha. These 3 are not given, so we're going to have to solve for each of these individually, and once we have expressions for each of these, we can plug them back into this expression here and get the nice long one. So let's start by solving for tension. To solve for tension, we're going to focus our attention on this little mass right here, little lowercase m. I did not draw it in earlier, but if you recall, the problem did state that the object, it releases, the problem releases this entire apparatus from rest, and then it falls this distance y in a time t. Well, if it starts from rest, and you know for certain it falls that distance in time t, you can use kinematics to solve for acceleration. And so that will help you solve for alpha. But let's just slow down and just solve for tension first. And to do that, we'll just sum our forces. We'll do, down is the positive because, that's the direction of motion. And so we'll do mg minus t equals ma. And once you simplify that, solve for t, you get t equals mg minus ma. Let's factor out the m. You get tension equals mg minus a. A is still not given, so we are going to need to find what A is. And so luckily we can just use kinematics since we are given enough information. Initial velocity is 0. You don't know final velocity. Acceleration is unknown. That's what we're solving for. Time is given as just t. And displacement is just given as y. So if you use this kinematic, Vf, I'm going to give myself some space. Velocity final is initial velocity plus at. Initial velocity is 0. You can solve for acceleration, and it comes out to be a equals 2y over t squared. Just plug in the stuff, solve for a, and this is what you get. So let's put a back up here. So tension is actually mg minus 2y over t squared. Now this is something we can use in our final time when we plug in. So we solve t. Next, we gotta solve for moment of inertia or alpha. Let's start by solving alpha because right off the bat, alpha is a over r. So since you just solved for a, alpha is simply 2y over t squared over r. Just 2y over t squared over r like that. This is alpha. And so you solve for that. Now you gotta solve for moment of inertia. Solving for a moment of inertia is going to be a lot weirder because this spool is unlike most solids because it's not exactly a hoop and it's not exactly a cylinder. It's a hollow cylinder sort of thing, or like a disc with a hole, or a cylindrical shell. So we don't really have a formula for it. So if you just go online and search up a moment of inertia formula for a hollow cylinder, you'll come up with this. This is the formula for the moment of inertia of a hollow cylinder, which is our spool in this case. So it's going to be I equals 1/2 m r1 squared plus r2 squared. Well, what's r1 and r2? Well, r1 is going to be your external radius, and this is going to be your internal radius. External radius is basically what we're going to call from the middle to the edge, so that's just going to be r. So you get half. And I hope this makes sense to you because it's the center all the way to the external. So that's what that means. That's why, which just means the whole r, the whole radius. So it's going to be 1/2 m r squared plus the internal radius, which is from the center to supposedly the axle. It's the center to the axle, which is given as r over 2 squared. And so you simplify this and you get moment of inertia is 1/2 m 5r squared divided by 4. Simplify that further. And your moment of inertia is 5 mr squared over 8. Nice. And these are your 3 unknowns. And now all we gotta do is plug it back in there. All right, let's start plugging. So t, and I'll find t up there. So m, let's start writing this. We'll do mass times the radius r because that's right there. And then we're gonna copy this entire, g minus 2y over t squared. And that does it for tr minus moment of inertia, which is gonna be 5. I'm gonna take out the number 5, the fraction 5/8. m squared multiplied by alpha, which is this. So 2y over t squared over r. And so before we move on, let's cancel 2 and 8, so you get 4 there. Let's take out an r, because we can. And let's rewrite this in a little bit more simplified fashion. This is supposed to be g, that's my handwriting, minus 5 over 4 m r y t squared. And this is supposed to be big M, and that's lowercase m. Again, I apologize for the handwriting. Let's continue. And if you look in the book, they want you to make it look something like that. So let's try and match what they got there. So if you want to get what they have, we can factor out r, as you can see. So let's do that. All right. So once you factor out r, you get that, g minus 2y over t squared. And if you want to match it exactly, they pulled out the m right here, and then they put the fraction back in there. They put the y there, and then it's just over t squared. And that's how you do problem number 69. Take it from here to here. You have everything you need. It's just a matter of formatting it the same way the book has it. This is problem number 69.